Welcome back to Nexperia Power Live. You're watching our Automotive channel. We're about to start with our second session of the day.
Here, live with you, are Nandor and Richard, who will cover key considerations design engineers need to be aware of when designing these products into their system, and how to fully utilize the benefits of repetitive Avalanche MOSFETs. The session will take about 25 minutes. We will start with a presentation and then take your questions. You can ask your questions using the question pane on the right-hand side of your screen. The questions are anonymous. So please ask your questions to our experts or share your own experience and insights. And with that, I will hand over to Nandor and Richard to begin. Gentlemen, the floor is yours.
Hello, everybody. Thank you very much for joining today. Today's session on automotive MOSFETs for repetitive Avalanche, MOSFETs being application-specific MOSFETs. And the topic specifically we'll discuss is how to maintain reliability and performance in automotive applications using repetitive Avalanche MOSFETs. I'm Richard Ogden, International Product Marketing Manager here at Nexperia.
And hello, I'm Nandor Bodo. I'm an automotive MOSFET application engineer at Nexperia.
And today we're going to cover 5 topics for you. So firstly, what is Avalanche? Application fit and portfolio. I'll then hand over to Nandor, who will cover enhanced data sheets that we have with these products and go through some worked examples of how this fits within your applications and topologies. We'll touch upon design and support tools, and then we'll open up the floor for some Q&A. So let's start with, well, what is Avalanche? Well, if you look at a typical circuit here of driving an inductive load, you have the inductive load above the low side MOSFET. What happens for current to flow through both the inductor and the MOSFET, you need to turn it on. So you apply a signal across the VGS of the device. This opens up the channel and allows current to flow through both the inductor and also the MOSFET. However, you will reach a stage where you need to turn that off through each cycle that you go through within the system. And what happens is when you turn that the low side MOSFET off, the energy in the inductor needs to go somewhere. The inductor starts behaving effectively like a source of energy. And what will happen is it will pull the VDS of the MOSFET beyond its breakdown voltage and force the device into avalanche. So it will effectively then dissipate that current that's created in the coil through the channel of the MOSFET. Now, typical for in these applications, you have 2 forms of avalanche. You have single shot and repetitive. Now, single shot avalanche is, as we say here, a random occurrence of overvoltage transient or fault conditions. So in every automotive system, be it on the powertrain, be it in chassis and safety, or even body control style applications, you have to design for a fault condition or that occasion when things go wrong. So this is, let's say, a single shot event like we say here. It's possibly the result of failure within the application, so not necessarily a failure within the MOSFET, more within the general application, so another component. And it is a low frequency of occurrence during both the MOSFET lifetime, but also the module lifetime. If we then compare that to repetitive avalanche, this is an avalanche event that's designed into the application. So rather than it being a random occurrence, it's hardwired into the design of that specific application and how it functions. So what happens here is the MOSFET can be expected to go into avalanche on a regular basis for numerous cycles. So we could be talking thousands, hundreds of thousands, millions to hundreds of millions of times. So if we just take a look at the typical kind of applications that you would use for driving a solenoid. So we've talked a lot in this example that we've worked through of inductors. A typical inductor is a solenoid or an actuator. So we've got an example here of the 4 different ways to control a solenoid. So the example we have here is an engine management system. And the 4 ways to control that are through a boost circuit, a freewheel circuit, active clamp, and then the repetitive avalanche or avalanche design. So if we start quickly with the boost circuit, this is typically the most efficient in terms of the energy that's used per cycle inside the module. You see a high number of components on there. You see that there's a boost MOSFET, there's recirculation MOSFET, there's lots of additional diodes inside there. So it's a high cost and high complexity circuit, but does give you the best overall energy efficiency. We then move into the freewheel circuit, which is the lowest efficiency and also associated with that lowest cost and complexity. The reason for this is we are using freewheel body diodes inside the circuit to reuse that energy that's generated during the cycle that the module goes through. Next, we have active clamp. So this has a high side and low side MOSFET inside the circuit. Again, we're driving a solenoid here. What happens when the energy turns off is the voltage across the inductor will increase to a certain point that it forces the Zener to break down, and this will turn the MOSFET, as you can see here, between the across the high side of the inductor and the gate of the MOSFET. It will exceed the switch on voltage and turn the MOSFET back on. Now, it's critical to point out here that timing is critical for this this style of design, because you need to ensure that you're within the MOSFET safe operating area, because you are turning the MOSFET back on. This is more efficient versus the freewheel topology that we've just discussed a little earlier. If we then move on to Avalanche, we see, I would say, a similar efficiency to active clamp. You see, firstly, there's a significantly fewer components on the board. It's the simplest design and lowest BOM cost. The reason being is we force the energy that's generated in the inductor through the low side MOSFET that you see here, and then it dissipates through the components. So what that means is that if you look across the various circuits here, you see simple design, as we say, a lower BOM cost, and subsequently, if there's fewer components on the PCB, it can support a smaller module size and significant system level savings towards our customers. If we then just briefly touch upon a typical application fit, so again, we've got the same circuit that we've just talked about. Across the x-axis, we have load inductance in henries, and then on the y-axis, we have peak current in amps. And the portfolio of products that we have available cover, we say, that the four major solenoid applications that there are in the car. So these are fuel injection. So the direct example that we've just shown of the fuel injection circuit. We have the engine control unit, so more of the peripheral applications that you would see around the car that are still inside the engine controller, things like the auxiliary heating and some of these functions. Transmission control, which is relevant for in automatic vehicles where you're switching through the various gears in the car. We use typically in automotive solenoids to help support that switching function. And then finally, the ABS valve. So this is typically in all modern, especially European cars now, you have the assisted braking system, whereby if you have an event where you need to apply a lot of pressure onto your brakes to slow your car down, and you feel that slight release of pressure, that is the solenoid inside that circuit relieving that pressure and stopping you from skidding. So these are let's say, the typical application fits that we see for these repetitive Avalanche MOSFETs. And so just to briefly touch upon the overall value proposition. So we've talked a little bit about the application fit, how the product works. But what we have is we're bringing this compelling modern trench style technology inside our LF-Pack family of products. So it has all the benefits that we have with our high robust, high reliability LF-Pack packages for automotive, and all the benefits that we have in manufacturing and robustness. But we also bring this 30 degrees C TJ rise technology that Nando will talk us through in the subsequent slides, that are very different than non-Avalanche technology. Silicon technologies that only have a 5 Kelvin or a 5 degrees C rise. We have tested it to 1 billion Avalanche cycles. And as I mentioned, it has the enhanced data sheet. So we've got a range of 4 products here, predominantly across the 60 volt range, because this is where we see the biggest fit in the market. But there's also a fit at 40 volts for a more focused support on transmission systems. And the main benefits that it brings, we would say, the automotive customer base, it's proven technology, very simple products to use, lower BOM count, and again, that significant system level saving that we've touched upon. So now I'll hand over to Nando, who will talk us through the enhanced data sheets and some worked examples.
Thank you, Richard. So all reputable data sheets have a single shot avalanche curves. These lines guarantee MOSFET functioning if a single avalanche pulse is applied at a junction temperature of 25 degrees. There is an additional curve for 150 degrees However, as Richard noted, some applications use the MOSFETs in Avalanche on a regular basis. To give guidance for these applications, a third line limit is included for repetitive avalanche rating. However, this limit is very conservative and does not reflect the real capabilities of the MOSFETs in repetitive avalanche applications. It's based on 5 Celsius junction temperature rise only. So in turn, Nexperia's repetitive avalanche application-specific MOSFETs provide a better insight into this capability. It's based on a 30 degrees increase, and a safe operating area is drawn based on the current and time of avalanching. And then a couple of points are selected on the border of the safe operating area, and from the devices are repeatedly avalanched at these conditions. From these tests, the cycle limit graph is produced by employing sufficient margin under the points of failure. So these two graphs in turn provide sufficient information for the engineer to do his calculations, to implement the MOSFETs into his application with certainty that it will not fail during the lifetime of his product. However, it needs to be noted that there is a penalty in terms of RDS-on increase during the lifetime of the MOSFET. So for example, at 10% of the intended number of avalanche cycles, there is about 25 to 27% increase in RDS-on, while by the end of the life cycle, there will be about 45% increase in RDS-on. So let's go through some worked examples. But first, we'll just go into a bit more detail in how solenoid drives work. So here we see a solenoid depicted as an inductor with a movable core. The movement of the core is determined by the current of the inductor, causing a force and an external spring that will pull back the core. The operation is similar to relays and other inductive actuators, but instead of applying a simple square voltage waveform, we control the current of the solenoid. So to set the core in motion, we apply a large current, and then to keep it in motion, again, a pretty large current is applied. And once the core reaches its destination point, a lower amount of current can be applied to hold it at that position. So these currents are regulated by this switching FET, but at the end, the turn-off is actually dictated by the bottom selector FET. So what happens is that we do have this current flowing through the inductor and the FET is turned off. And because the inductance still wants to pump this current, it starts behaving as a source and has some voltage across its end. This voltage is then transferred to the FET via this diode, and the voltage rapidly increases until the FET reaches its avalanching voltage and breaks down. So eventually the inductor can get the current through down to ground, but at a significant cost of voltage and therefore energy as well. So the current will decay in a pretty fast manner. So usually the switching FET supplies a number of solenoids and selector FETs, while the selector FETs itself chooses which solenoid will be the actively drive one. So let's see an application example. Let's consider an application driving a 3 millihenry solenoid with 1 amps at 3 kilohertz. So this 3 millihenry is really just the model of the solenoid drive. Actually, the inductance changes as the core shifts within the solenoid, but we're interested in the inductance at the end position of the core. So we take the current and apply it to the first figure, and we can see that the avalanche time can be up to 200 microseconds. By using calculation and simple inductor equation, we can see that the avalanche time should be much less than that, so we are safe there. The next thing that we need to do is to calculate the energy that is contained in the inductor, and that will be at the same time the energy that's dissipated in the MOSFET. And applying that energy to the second graph, we can see that we would be allowed to do something in the order of 4 billion cycles. And then the last thing to design in is to make sure that the junction temperature stays below 175 degrees. The junction temperature is the sum of the ambient temperature, temperature rise due to conduction of the MOSFET. The third thing is the settling temperature from the previous avalanching event. So that can be tedious to find. And the 30 Celsius rise of the current avalanching event. This can be done by hand, but also maybe it's preferable to do through simulations, as we'll see later on. A more demanding application is depicted here. So we use now a stronger FET. The previous one was about 52 milliohm MOSFET, and this one is a 13 milliohm. The inductance stayed the same, but the current is now 4 amps, which is considerably higher for a solenoid hold current. And we can see that although the time interval and the energy have increased substantially, we still have over 1 billion cycles till the end of the lifetime of the device. So here is a thermal simulation, and this simulation can be found on the link that should be in the description below the video, and it is hosted on a web by a free simulation tool called PartQuest. It allows engineers to select the MOSFETs and observe the junction temperature along with any other waveforms really that appear. So this voltage source here dictates the shape of the current by comparing its output with the current waveform that is fed back from this resistor. And then the MOSFETs themselves can be selected from a drop-down menu in the tool itself. Almost all Nexperia's automotive MOSFETs are available online to just plug it in. If the model of the MOSFET is not available, there's always the option to include from a SPICE model that can be downloaded from the website. And then we have a thermal model as well. Here below is the custom thermal model of the PCB, and above is the model of the MOSFET itself that can be also obtained via the website or on demand from Nexperia. So the red trace here represents the junction temperature of the MOSFET, and we can see that at the avalanching time there's a substantial jump, and we need to make sure that the peak of that jump is below 175 degrees, and as well as the jump does not exceed the design 30 degrees. So I'll hand back to Rick to take us through the materials available online.
Thanks, Nando. Yeah, so thank you for joining the session. There's various materials available online, so please do visit nexperia.com/MOSFETs for, again, application-specific MOSFETs. On there, you'll find all the tools that you will need to help you design these components in, so data sheets and a way to order samples appropriate to what we've discussed. As Nando has just mentioned, there will be interactive application notes. This is a specific interactive application note available on nexperia.com. That is IAN 5003, driving solenoids for automotive applications. There's various news and blog articles for you to peruse. And of course, we also have quick learning videos where we talk through the first two videos you see here are a more detailed explanation of the main discussion points we've been through today around how to select your MOSFETs for automotive applications, 4 ways to control automotive solenoids, and then finally single-shot avalanche ruggedness of MOSFETs. So I think that brings us to the end of the presentation and opens the floor for questions and insights. Thank you.
All right. Thank you very much, gentlemen. Great stuff. We definitely have a couple of questions for you. These enhanced data sheets are better than the previous ones, but how far do the avalanche curves match with testing results?
So that's a good question. So there is a certain amount of derating that we've captured inside the data sheets. So they do match the true capability of the product based on the testing that we carried out. So maybe just to embellish a little bit on that. So during the qualification process, we follow the typical Q101 process to qualify these devices, but we also created a bespoke tester to allow us to test these products to that billion avalanche events that we mentioned a little earlier in the presentation. So it's been an incredibly rigorous process for allow us to create the data sheets, and it is, I would say, reflective of the true capability of the product, even with a small amount of derating to give us let's say, a headroom for the kind of applications that these products will go into.
All right. Then the next question, what is the diode in parallel to the inductor doing in the avalanche mode circuit?
Nando, do you want to answer this one?
Yes, sure. We can go back. Well, yes, say this slide. This slide will do. So the diode allows for the repetitive avalanching event to take place. So once the MOSFET blocks the current, the inductor will develop a voltage that is in reverse. So it will go to the negative, and the diode will start conducting, and due to that, that voltage across the inductor itself will be transferred to the MOSFET and take the MOSFET into avalanche.
Okay. Then a question about slide 17, if we go back to that one. How is the 78-volt avalanche voltage assumed?
Yes, the 78-volt avalanche voltage is assumed as 30% over the drain source breakdown voltage of the MOSFETs, which is 60 volts. This can be. This is an assumption. It's better to measure the MOSFET avalanching voltage.
Yeah, that's the typical breakdown voltage of our trench MOSFETs, about 30% higher than the VDS rating of the product. So that's just the nature of how we create the devices. So that's kind of where that comes from.
Okay, great. Let's take one more question. On slide 19, how is the current waveform generated in the tool?
So the current waveform is fed back. This is a current sense resistor, and it's not shown, but its top is connected to the input of this operational amplifier. And basically there's it regulates the operation amplifier, controls the MOSFET so that the current is according to the voltage reference that is supplied to its positive input from this voltage source. So it's a simple feedback loop.
Okay.
Good. So that brings us to the end of the live session. Thank you to Nando and Richard. And if you still have questions, you can always use the chat box to ask your question. And if you want to know more about MOSFETs, you can follow the research link underneath the screen, or as mentioned just now, chat to one of our power experts. And we have one of our new interactive application notes on this topic. And these interactive application notes are a new tool from Nexperia designed to give engineers a hand-on approach to design testing, which are available on nexperia.com.
Please stay around. Our next live session on paralleling MOSFETs in high-power applications will start after a short break.